Section 6.5 is on page 270, talks about impulse function. That's one of the most used applications that we have. Consider the effect on a system modeled by a differential equation by a forcing function which acts for a very short time interval, like a current in a circuit. An airplane making a hard landing. When the tires hit the ground, they hit the ground. The first hit is not for that long. A ship hit by a single high wave. A tennis ball being hit by a racket. So, there are a lot of things like that where you're only using this function for a very short period of time. Consider a unit step function. Switch on when t equal a and switch off after a short period. K is a very small value, and I'll show you why it has an amplitude of 1 over k. And this is the function right here. This is how the function is defined. F sub k of t minus a turns on at a. It becomes 1 over k. So if this is 1 over k, and this turns on right there. So it's 0 anywhere else. Once you get to a, you're up there. And it stays as 1 over k until you hit t equaling a plus k. It shuts down. And if you take this area, you'll notice that this length right here is right minus left. A plus k minus a is k, and the width is 1 over k. So this area is k times 1 over k, which is 1, and the 1 stands for 100%. Alright, and that's how this function is defined. And the impulse of the force function, I sub k, is the integral from 0 to infinity, f sub kt minus a, because you're shifting that by a units instead of starting at 0. And this function is simply 1 over k, and we want that area to equal 1 all the time. We're not going to get into the derivation because you don't need to know that, but you need just to use it. As k gets smaller and smaller, we take the limit as k approaches 0 of f sub k, this function, and that gives us the direct delta function or unity impulse function. On the table number 17 tells you how to transform using the plus. And here's the catch. If we're going to undo it, we are going to use property number, what did we use on the previous section? When you go back from e to the negative ct, we are going to use property 12 to undo direct. So directly you use direct to really apply the Laplace, but when you undo it, there is no direct in there. There is the unit function, or the unit step function, some people call it, whatever you like. So if I look at this problem, I notice that, well, two problems. Let me look at the first one. If I look at the first problem, and we're just going to focus on part A because part B and C, they require to use software. We're not getting into software, we're not there yet. Page 273. Find the solution to the given initial value problem. What we do, we jump straight at it. We apply the Laplace on both sides. And this will give me, and those are 0, so I already know how this works. This is going to be s squared times f minus s times 0. I'm just writing that for your notes, minus 0. Right? Plus 4 times f of s. Or the left is simply s squared, or I could say f of s into basically the characteristic equation with s in place of x, what we used before, or r, whatever you want to call it. The right side, when I apply the Laplace on this by 12, this is going to be e, and notice, if this is minus, this is minus, so this is minus pi s minus e to the negative 2 pi s. And that's all the tricky part in this section, and that's the application. You'll be surprised how this works. So if I look closely at this, this is e to the negative pi s minus e to the negative 2 pi s. So if I take f sub s, that's simply e to the negative pi s divided by s squared plus 4 minus e to the negative 2 pi s divided by s squared plus 4. If I continue right there, and if I rewrite this just to match, and I'll show you what that means, leave e to the negative pi s out of it. I'm looking at 1 over s squared plus 4 minus e to the negative 2 pi s times 1 over s squared plus 4. If I look at the table and I work my way backwards, I'm looking at 1 over s squared, 1 over s squared, it was s squared, I lost track, 1 over s squared plus 4. So if I look at which of those is going to really do the trick for me, I notice 1 over is matching this. There's only one minor difference. It says s squared plus 4. What do you square to get 4? 2. You need a 2 up there. I need to make that adjustment. So that's a simple fix. I could multiply by 2 and divide by 2, multiply by 2 and divide by 2, and now I could say, you know what? Apply the inverse Laplace transform. Now it matches the table. And I can get the solution to this differential equation to be e to the negative 2 pi over 2. This is going to give me u, right, sub pi t, right? And this right here is supposed to give me, did we say sine or cosine? Sine of at is supposed to give me the sine of at. A is 2, but because of this shift, it's going to really be t minus pi minus e to the minus u to the 2 pi t over 2, and the same deal here. This is going to give me the sine. Instead of 2t, it's going to be 2 times t minus 2 pi because of that shift. And that would be my final solution. And what I just did, I solved an actual application in differential equation by just using Laplace table. Now I do want to point out, the table is really using the integral, but since Laplace figured out that you're using this a lot, he came up with that table that saves you a lot of work. There we go. And that's basically it. And this is, we said, by 5. So I would like you to write by 5 on each of those, please, on the homework, and specifically on the exam. This way I can make sure that we're doing this the way we should. We're going to apply the same deal here. We're going to apply the Laplace on both ends. And they're making this for simplicity 0. So, you know, automatically I know I'm going to get s squared times f of s plus s times f of s plus 3 times f of s. And when I apply the Laplace on a sine, I'll get 1 over s squared plus 1, and this is by 5, I just did that, plus, and if I apply the direct by 17, which is what this section is all about, this is going to simply give me e to the negative 3 pi s. And now if I factor an f of s, I will get 1 over s squared plus 1 times s squared plus s plus 3. And it's no big secret. It's, oh, there's a 2, huh? Look at that. It's right there. So that's a nice way of thinking about it. Every time you get this, it should match the characteristic equation. Plus e to the negative 3 pi s divided by s squared plus 1 into s squared plus 2s plus 3. And the tricky part here again is figuring out, it turns out the busy work, where does 1 over s squared plus 1 into s squared plus 2s plus 3 come from? And that's a bit of work. I am going to complete the square on the second piece, but as far as the work is concerned, that's as plus b, and this is cs plus d. How quickly can I find a, b, c, and d? And to save time, we already know how to do this. I'm going to tell you what they are. And I got a to be negative 1/4. I got b to equal 1/4. I got c to equal 1/4. And I got d to equal 1/4. What do you know? That's really what it turns out to be. So basically, what this says, f of s is actually 1/4 times. If I put a 1/4 there, 1/4 there, 1/4 there, and 1/4 there. If I take the 1/4, they're all 1. So that's really s plus 1 over s squared plus 1 plus e to the negative 3 pi s over 4 into s plus 1 over s squared. Oh boy. Okay, I left the whole chunk. Trying to do this a quick way. Plus s plus 1 over s squared plus 2s plus 3. Let me shift that a bit to the right. The beauty of technology these days. Plus s plus 1 over s squared plus 2s plus 3. And the reason we have to do the completing the square, this doesn't factor. So I'm really looking at f of s equaling 1/4 times s over s squared plus 1. That's easy. That's a cosine. That's by 5. By 6, this is a sine. But here, this is really s squared plus 2s. Now, I need a 1 out of that. So that's really s plus 1 squared plus 2. So this is s plus 1 over s plus 1 squared plus 2. It worked out nicely. Plus e to the negative 3 pi s over 4 into s over s squared plus 1 plus 1 over s squared plus 1 plus s plus 1. Here the shift matches. If it didn't match, I would have had to modify it like I did the previous section. Oh boy. Okay, plus 1, plus 2. So, if I really think about this carefully, I could say, if I take the inverse Laplace transform, they're going to be almost identical, except one of them has a shift, one doesn't. S over s squared plus 1, that would be, I apologize, I got a to be negative 1. I forgot about that. So negative 1/4, that's a negative s, right? So that's negative and a positive. That's a negative s. So that's a negative and a positive. Okay, so this is going to be negative. This is the cosine of 1t, and that is by, let me just get that right, cosine 6. That's by 6, plus the sine of t, that's by 6. Here, if I really think about this, and let me shift this down just a bit so I could box it nicely. If I take e to the negative t, wouldn't that make this s over s squared plus 2? So I really need to multiply this by radical. Oh no. If it's a cosine, it doesn't need it. So this is going to be the cosine of what do you square to get a 2 radical 2t, right? This is also by, I use 6 on both of them. This is 5. This is by 6 with the shift. You could also, if you want, refer to the actual number on the table. You could actually talk about 10. I wouldn't mind either way, but this is really 10. And that takes care of the first piece. The second piece is going to be identical. It's going to be 1/4, except there's a u of 3 pi of t, right? And that's going to really yield a negative cosine of t minus 3 pi plus the sine of t minus 3 pi times plus e to the negative t minus 3 pi times the cosine of radical 2 into t minus 3 pi. And that would be my final answer. So you only need to write the numbers on the first one because the second one matches with simply a shift, nothing more. Okay, I see a mistake I made. I'm so sorry. This is so embarrassing. This was over s squared plus 1. This wasn't. This was over 1. So when I did this, this didn't. This is only that right there. This doesn't have that second piece. Right? You guys are supposed to tell me these things. So here, that's the only piece that you get, right? No. I went about it the wrong way. Forgive me. Okay, I could fix that quickly. So this is really gonna have, when you divide, you're gonna only have s squared plus 2s plus 3, right? So this really doesn't pick the 1/4 because it doesn't have that. It's really e to the negative, and I'm debating if I should redo the video or not, plus 1 squared plus 2. Okay, that's okay. No need to do that. This is simple enough. E to the negative 3 pi s over s plus 1 squared plus 2. So, boy. So this piece actually is a lot smaller, a lot. This is u sub 3 pi of t, right? And if I take e to the negative t minus, it should be e to the negative t, but I'm going to shift that by 3 pi. That makes this 1 over s squared plus 2. And you do notice on here it was s squared s, so it wasn't a problem. S doesn't need that shift by 10. But if you look closely at number 5, number 5 requires, what do you square to get the 2? Radical 2. You need to multiply by radical 2 top and bottom. And that gives you the sine. It should be of radical 2t, but it's going to be t minus 3 pi because of the shift. Okay, now it's a lot better. Wow. Sorry about that. Hopefully that didn't confuse you a lot. And if it did, we could talk about it in our discussion, right?